This Explain Everything video is intended to accompany Worksheet 1 in Unit 10. In chemical reactions, we conclude that there is a change in structure in the system when there is a change in temperature. Heating, Q, is the mechanism by which the system exchanges energy with the surroundings. We're now ready to investigate the question, what changes occur in the system when radiating, R, is the transfer mechanism? Examine these infrared security camera images. What is the relationship between the temperature of an object and the intensity of the radiation it emits? If you don't have access to an apparatus that allows you to vary the energy supplied to the filament of a light bulb, you may use the next few slides to help you answer question 2. Displayed here is a variac, or variable power supply. At this setting, it supplies about 10 volts to this display bulb. Note that the filament is barely glowing. You may be able to tell that it's a reddish-orange color. Now the variac is supplying 20 volts to the filament in the bulb. You should note that the intensity of light emitted is greater. If you were able to observe this directly, you would notice that the light emitted is more yellow-orange than before. It is very difficult to capture these color differences without reducing the exposure so much you couldn't see anything else but the filament. Here the variac is supplying 30 volts to the bulb. What changes do you notice in the light emitted by the filament? You should now be able to answer question 2 in the worksheet. To more closely analyze the light emitted by the filament, a spectrophotometer is needed. Here a Vernier GoDirect SpectroPhys Plus with an optional optical fiber will be used. Light from the filament is directed to the SpectroVis, and the spectral analysis software breaks the light into its component colors. The next few slides show the emission spectra when the filament is heated to various temperatures. This is the spectrum when the variac is at its lowest setting. Know that the graph is a plot of intensity versus wavelength of light emitted in nanometers. The second trace is the spectrum when more energy is supplied to the filament and it glows orange. Here, the third trace, when even more energy is supplied to the filament, is shown. Heating the filament produced some change in the structure of the matter that was responsible for the light emitted. But what structural change could have occurred? The filament, an atomic solid, was still a solid. Certainly the atoms were moving around faster, but perhaps some change was occurring inside the atoms. Could the movement of electrons be involved in some way? When the filament gets even hotter, the light emitted appears white to our eyes. The spectrophotometer reveals that light from the blue end to the red end of the visible spectrum is emitted, although the output is stronger toward the red end of the spectrum. You should now be able to answer questions 3 and 4 in Worksheet 1. Here, the incandescent display bulb has been replaced by a compact fluorescent bulb, or CFL. Energy from the variac excites the atomic gas inside, which emits light that is noticeably cooler than the light emitted by the heated filament. The spectrum of the light emitted by the CFL is markedly different from that emitted by the heated filament. In this image, the spectrum of light emitted by excited mercury vapor is superimposed on the spectrum of the CFL. The overlap of the dominant peak in both spectra is good evidence that the CFL contains mercury vapor. This peak in the yellow-orange region is due to light emitted by the phosphor coating in the inside of the CFL. This helps make the light emitted more pleasing to the eye. You now have enough information to answer questions 5 and 6 in Worksheet 1. Let's summarize what we've learned thus far. An input of energy is required to make atoms emit radiation. Unlike the continuous spectrum emitted by an atomic solid, an atomic gas emits only certain energies of light. The Thomson model of the atom, with its electrons embedded in a sphere of positive charge, is inadequate to explain this phenomenon. A better model is needed.